Hello, and in this latest video in the AC Power series, I want to talk about the maximum power theorem and how it relates to AC circuits. Now, I hope you remember the maximum power theorem when we derived it for DC circuits. It looked something like this. The problem to be solved is, if we have a source with a Thevenin equivalent voltage of V and a Thevenin equivalent source resistance of R1, then the load which dissipates the maximum power in the load occurs when the resistance of the load is equal to the Thevenin resistance of the source. So in this case, if you set R2 equal to R1, then you are extracting the maximum possible power from this source. So, how does this apply to AC circuits? Well, it's almost the same, but not quite. First, I just want to remind you that you can apply Thevenin just like you can apply any of the theorems and formulas we derived for DC circuits to linear AC circuits with sinusoidal sources. All you have to do is convert the voltage and current sources to their phasor representations, convert the impedances of the resistors, capacitors and inductors to their complex impedances, and just apply all the same algebra that we did previously, and all of the shortcuts that we took, including Thevenin, are equally applicable to AC circuits. So, in this case here, we have an AC circuit going at 1 MHz with a voltage source here that we can represent by a phasor of just 1 volt, and that would produce this. And we do it in exactly the same way that we derive a Thevenin equivalent network for a DC source. We work out the open circuit voltage, which you can get from the potential divider equation in this case, and we set the sources to 0 and work out the impedance between A and B. And in this case, that would just give us the 100 ohm resistor in parallel with a 1 nanofarad capacitor. If you then do the calculations, putting in the frequency of 1 MHz and deriving the complex impedance of the 1 nanofarad capacitor, you end up with this Thevenin equivalent network. And the Thevenin impedance now, it's an impedance, not a resistance, of 84.7 and a phase angle of -32 degrees. So, the AC maximum power theorem is applicable to any network which has two terminals and has linear components. That leaves us with this problem. What load impedance L should we put onto the output of a source which has a Thevenin impedance of Z in order to extract the maximum power into the load? And a first guess might be to say, well, the maximum power theorem for DC says that the load resistance should be equal to the source resistance, so perhaps L must be equal to Z. No. Doesn't quite work like that. To see why, we have to go back to the analysis of where the maximum power theorem came from. Let's have a go at analysing this circuit. We have a voltage source here represented by a phasor V. We have a source impedance Z and we have a load impedance L. What is the active power that's dissipated in that load impedance L? Okay, we know that the complex power, S, is given by the current flowing through the network, or its phasor representation, modulus squared, times the impedance, in this case our load impedance L, divided by 2. That's the complex power. The active power is the real part of that. Now, the real part of L, we could write that as, well, let's write L as its real part, Lx, and an imaginary part, Ly. And similarly, we'll do the same thing with the source impedance Z. We'll write Z in terms of its real part, Zx, and its imaginary part, Zy. Now the active power, the power that's actually dissipated in the load, we could write as the modulus of the current squared divided by 2, because those are just both real quantities, The real part of L is L of x, so it's just equal to that. How do we get the current? Well, that's the current phasor. The current phasor is the voltage phasor divided by the complex impedance, and the total complex impedance in our network is Z plus L. So the current phasor, I, would be the voltage phasor V divided by Z plus L. We want the square of the modulus of this. Well, if we take the modulus of I, that's just the modulus of V divided by the modulus of Z plus L. And the square of the modulus of I is the square of the modulus of V divided by the square of the modulus of Z plus L, which is, well, the modulus of Z plus L will be the modulus of Z, which we could write as Zx plus jzy, plus L, which we can write as Lx plus jl of y, and all that gets squared. If I write that collecting the real and imaginary terms like this, I could say it's the modulus of Zx plus Lx plus j times zy plus ly. Right, think about this on an Argand diagram. The total complex number, represented by that denominator there, has a real part of Zx plus Lx and an imaginary part of Zy plus Ly. So the complex number is going to be somewhere around about there. The modulus of that complex number is the distance it is from the origin, and the distance it is from the origin, that just comes from Pythagoras in this right-angled triangle. We could write this as Zx plus Lx squared plus Zy plus Ly squared. That's the square of the modulus of this complex number. It's the square of the distance of that point from the origin. Right, that is the modulus of I squared. To get the active power, we have to take this term, divide it by 2, and multiply it by the real part of the load impedance, L. So that's just Lx over 2. That is our active power. And that is the expression that we want to maximize. How do we find a value of L, which means getting a value of Lx and a value of Ly, the real and imaginary parts, to maximize this value of P? First thing we can tell, what should the value of Ly be? Well, Ly only appears in this expression once, and it appears in the denominator there. If I want P to be as big as possible, I need the denominator to be as small as possible. This term, however, is squared, so it cannot be negative. The smallest value it can possibly be is 0. Now, if I take this and say, at what value of Ly is this term here going to be its minimum? The answer is Ly has got to be minus Zy, because in that case, this term here disappears. I get 0 squared. That makes the denominator as small as possible, and therefore my power as large as possible. So I can work out what the imaginary part of my load impedance has to be quite readily. To work out what the real part, Lx, has to be, I have to do a differentiation of this. I can simplify this formula now because I know that Zy plus Ly is going to be 0 at the point of interest. So I can have P equals modulus of V squared Lx over Zx plus Lx squared and 2. And I want to know what value of Lx gives me the maximum possible value of P. Well, that's a differentiation looking for a turning point. Well, this is a differential of a quotient, so it's the term on the bottom times the differential of the term on the top, which is just modulus of v squared, minus the term on the top, v squared times lx, times the differential of the term on the bottom, which would be 4 zx plus lx, divided by the square of the term on the bottom. But that doesn't really matter because I want this to be equal to 0. And the only way this is going to be equal to 0 is if this term is equal to this term. So I've got zx plus lx squared times 2 times modulus of v squared minus the modulus of v squared. Well, these terms have to be equal, so equals the modulus of v squared times lx times 4 zx plus lx. Okay, well, that 2 cancels out with one of the 2's in that 4, leaving a 2. The v squareds cancel out. That term cancels out with one of the terms in this squared, and that just leaves me with zx plus lx equals 2lx. Subtract lx from both sides, I get that. So those are my 2 results. Lx equals zx, Ly equals minus zy. The real part of my load should be equal to the real part of the source impedance. The imaginary part of the load should be equal to minus the imaginary part of the source impedance. In other words, the load impedance should be the complex conjugate of the source impedance. And that is the key result for the maximum power theorem in AC. The load is the source impedance complex conjugate. We can see this working. Here I have a source, which is a 1 volt source, going through a source impedance of a 100 ohm resistor in series with a 1 microfarad capacitor. And if I just attach a 100 ohm resistance as the load, then the total power dissipated in the load, 765 microwatts. If I made my load have the same impedance as the source, that would involve putting a 1 microfarad capacitor in series with my load so that my load had exactly the same complex impedance as my source. And the power dissipated in the load, remember it's only resistors which dissipate active power, is 353.8 microwatts. However, supposing instead of that capacitor, I put in an inductor chosen so that the inductor has the impedance of the capacitor times -1. So I'm putting in an inductor which effectively cancels out the complex impedance of the capacitor. The power dissipated in my load shoots up to 1.25 milliwatts. And that's the maximum possible in this circuit. Another point to note is that when you do have this optimum load to get the maximum power from the source, it means that the current flowing through the circuit is in phase with the voltage source. And the reason for that is that the inductor here and the capacitor there are cancelling each other out. They have equal and opposite complex impedances. So the total complex impedance in this circuit is just 200 ohms. And if you think about it, that's kind of reasonable. You want the minimum possible impedance in this circuit to get the maximum current. With the maximum current flowing, you're going to get the biggest power being dissipated in this 100 ohm resistor. And the way to get the maximum current flowing is to cancel out the impedance of this capacitor with an impedance of an inductor in the load. So, quick summary. The AC maximum power theorem applies when you have a linear source with a source impedance of Z, and you get the maximum power dissipated in the load. That's the maximum active power when the load impedance is the complex conjugate of the source impedance. and you can go through and work out what that maximum power actually is going to be, and you'll find it's given by this. And that's all for this one.